for research are just dictated by your own curiosity and unlimited in what you can do. And I'm happy to answer questions. I think that was like 40 minutes, huh? Maybe 38?
Mm-hmm.
So a little bit long, but that's because you know. No, I'm kidding. So that's what I want to say to them. Is it too much? Is it too intense? Or does it give you a good feel, sort of? Even if you don't understand everything, do you think it gives you a good feel for what is going on?
Yeah.
Or do you think I should take maybe the polynomials out?
No, I think polynomials are nice. I mean, maybe if you can like continue with like some sorts of like, cause like I think if you can
This
like
is just this presentation for this. I'm asking for your feedback that I'm going to do Friday.
Yeah, if you can like add a bit of like stuff on, because you basically define a polynomial, but we're not sure what to do with it next. Mm-hmm. So if you can like,
I have no idea. That's the thing. What I wanted her to do, but she was more interested in studying different types of graphs and trying to find the polynomials. I have a polynomial, as those of you in my class know. I would like to put an x in there and get a number out, and then put that number in and get another number out, and then put that number in and get another number out, and see if there's some sort of something that happens. Or just understand, what does it mean if you put a number into this polynomial?
mm-hmm.
Right? What if I evaluate this polynomial at -1? Does that have some meaning with the graph?
Or at least like look at it like minima and maxima and all this like
minima, maxima.
Yeah.
And does that tell you something? Can you relate that back to the graph?
Yeah.
That's sort of something that I personally would be interested in. But so that's a good question. So what I could do is just say, what's next? Well, that's up to you. So much is unknown about this. I mean, there's a lot of little things, like if you have a certain connection, or if you look at degrees, you can kind of say what goes on with the degree, how many edges come out. There are things known, but this idea is new, and there's lots of open questions about it.
What would be an input for this polynomial?
like okay, at least we can know that like it always is like 0 if x is 0.
Yeah.
So what does it give us?
So if x is 1, it gives you the total number of zero forcing sets.
Yes.
Right?
Which is
overall sizes. Right?
And if x is -1, then it just gives you like the number of even minus the number of odd.
Oh yeah.
Yeah. But what about 5? Is there something that does that? Yeah.
But I mean,
so this is something that if I see a function, I want to put an x in it.
Yeah. But I mean, maybe you can just like talk about like factors of it, because like yes, you said like if we know how far are the roots of it from 1 and -1, we'll be able to know how like how fast is that graph in a sense.
It could be.
Because like the more sets of forces it has, it means like the more probability it has for like spreading the disease.
Mm-hmm.
So like so the closer the graph would be to like the more is this value of it at x equals to 1.
That's right.
Yeah.
That's right. Yeah. So I'll put a conclusion. So the cellular. So you can go if you want, or we can do some more little minor things.
Let's do something.
Gluttons. So you understand about. Do you know about binary expansion of a number? You know that if, so base 10 expansion, if I write 489, that's 4 times 10 squared plus 8 times 10 to the 1 plus 9 times 10 to the 0, right?
Yeah.
So you can do the same thing with base 2, except the digits can only be 0s and 1s, right? So this is the 2 to the 0 place, this is the 2 to the 1 place, this is the 2 to the 2 place, 2 to the 3, 1 to the 4. So this number, so 10110 base 2 is equal to 16, 22? 22 base 10. And you can go the other way, right? If I want to, so the powers of 2 go 1, 2, 4,
8,
8,
16,
thank
32,
you. 32,
64,
64.
198.
We're not going to need to go bigger than that tonight. So what if I wanted to write 47 base 10 into what it's equal to base 2? So there's lots of algorithms for it, but I just picked
0, 1.
the biggest power of 2 that's in 47. So this is going to be a 2 to the 5th, right? And then when I subtract 32, I get 15. So that's the 8.
It's just all of them at once.
But there's no 16,
Because
right?
it's 1 less than 16.
So this is 2 cubed, and then 2 squared. Now if I, that's right, so if I subtract 8, I get 7. So that's the 4, and then 2 to the 1 is 3, 1, 1, right?
1, 0, 1, 1.
Okay. So so for cellular automata, I showed you a 2-dimensional cellular automata, but there's a 1-dimensional as well. So I have a grid, a 1-dimensional grid, and I'm going to put the initial condition up here and the first iterate below it. So if I had a sequence of 0s and 1s, like that, then I want to know so I want to update all the cells simultaneously, although in practice we have to do them one at a time. And I want to update it depending on what its nearest neighbor's value is. So I have to have a rule that says, if this is a 1 and your neighbors are 0s, then you stay a 1. If this is a 1 and one of your neighbors is a 1, then maybe you turn to 0. Right? So we have to have a rule that says, if I have a block of 3, so this can either be a 0 or a 1, and then each of these can be 0s or 1s. So I just need to know what the update is. So how many configurations are there for making a rule?
8.
There are 8, right? Because 2 choices here, and then 2 choices for each of the neighbors, so 2 times 2 times 2. So there are 8 choices. So if I made 8 little blobs like that, and put every possible configuration down, I would know what the rule was. So there's a really nice base 2 systematic way of doing that.
Wouldn't the rules contradict in the case that you take a longer one? Because
So
you'll have sets of 3 like this, overlap.
So what do you do at the, oh no, they won't
Depends
overlap.
what order.
See, now I have 0, and so there's my new configuration. So I only care about what this one's new value is,
Okay.
based on its neighbors. But the question ought to be, what happens to this guy? Doesn't have a neighbor? So you can either do periodic boundary conditions, where you say, let's just wrap it around like this. Or you can say, you don't know, and just stop. So
Okay,
in our, yeah.
Okay.
But in our 700 by 700 grid, we use periodic boundary conditions. Okay, so what did I just hand out there? This is a way to make the rules for one-dimensional cellular automata. So you notice at the bottom one, I have every possible configuration of groups of 3. Those 3 numbers make a number in base 2. And they are in increasing order. So let me just say that a little bit. So what's going on here is, I have no idea. Oh, because I did something silly. So what's going on here is, these are blank, these are supposed to be shaded, because sometimes we like shading instead. So these are shaded ones. Can you see the shading on your, these are shaded. So one would be shaded, and, whoops, that's just wrong. But either way you like it is fine. So if I think about these little this three configuration as a binary number, then I've written the different configurations in order from smallest to largest, right? This is 0. This is just 2.
1.
I guess I'm starting, yeah, I'm, sorry. I'm calling this configuration 2 to the 0, the 2 to the 0 place. The number that goes here is being multiplied by 2 to the 0. The number that goes here is going to be multiplied by 2 to the 1. The number that goes here will be multiplied by 2 to the 2. So there's two different base 2 things going on. One of them is just looking at the numbers 0 through 7, right? This is 7. 1 plus 2 plus 4 is 7. So 0 through 7 are those numbers. I'm taking those numbers and raising 2 to that power. And then I'm going to say whatever number gets put here, like if I put 1, 1, 0, 1, 0, 1, 1, 0, then this would be rule number 1 times 2 to the 7, plus 1 times 2 to the 6, plus 0 times 2 to the 5th, plus 1 times 2 to the 4th, 1 times 2 squared, 1 times 2. That's the rule number it would be. And if we all agree to write the configurations in that order, then I can tell you any rule number and you will know what to do when I give you an initial configuration. So let's work through this a second. So let's write out rule number 85. So 85, do you have this done yet? Minus 64 is 21. Minus 16 is 5. Minus 4 is 1. So 64 is 2 to the 6th, I guess? 16 is 2 to the 4, 2 squared, and 2 to the 0, right? So those places will have a 1, and everything else will have a 0. So rule 85 is going to be 1, 0, 1, 0, 1, 0, 1, 0.
Well.
Right?
Did you say it from left end or from right end?
I'm sorry, say that again?
She started from the right.
Oh, okay.
Oh, yeah, you have to start from the right because smaller numbers are on the right
sure.
than bigger numbers. Yeah.
1, 0, 1, 0, 1.
So you can do whatever you want, but we have to agree on the order. Otherwise, if I say rule 85 and Jason says rule 85, we are meaning different things, right? But if we agree on the order. And this order was conceived of by none other than, any guesses? Who's the only?
You?
No, God, no. Stephen Wolfram. And he has a lot written on this stuff. So that's rule 85. How does this work then? Well, I look at my initial condition. Let's start for this number 0. its nearest neighbor is a 1 from this side over here. So this 0 has the configuration 1, 0, 1, which the rule tells me it updates to a 0. This one has configuration 0, 1, 0, so it stays a 1. Oh, this is really boring, isn't it? Really? Is this true? So this is a fixed point, right? Because it doesn't move. 0, 1, 0. 1. Yeah, that's very boring. So if we did another initial condition like 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, then we might get different stuff, right?
Mm-hmm.
Are there questions about how that works? Okay, so now what rule is this one, the bottom one?
141.
Oh, shh. So how do I figure out the rule?
Is black 1 or
Black is
is
1,
okay.
and yep, the shaded is 1 and the unshaded is 0. So this is going to be 1 plus 4 plus 8 plus 128. How many rules are there?
Oh,
I mean, infinite. It just you can keep taking.
You can't keep going. You only have 8 configurations.
okay. Oh, okay.
So how many different rules are there?
255.
How many choices do I have for this?
1.
2. I can have.
Okay.
Yeah, sorry. For a rule, I can have 2 choices, a 0 or a 1. How many choices do I have for this?
2, so it's like 2 in the power of 8.
255.
6. 2 to the power of 8.
Because 256 would go to the next one.
No,
But you can also
all
have
zeros.
0. Yeah.
Yeah.
So 256.
256, right? So there are 256 rules. There are some very interesting ones. Rule 30 is very particularly nice.
Why?
It looks really chaotic, and it looks like there are little Sierpinski triangles in it.
Woohoo!
So if we went and typed Rule 30, Cellular Automata.
Oh, you already searched it.
Yeah, that's Rule 30. So even with 1, 1 at the beginning, it spreads out, and do you see what I mean about the little Sierpinski triangles?
Yeah. Wow, nice.
And this is just, we could do this one by hand, right? That's just a few iterations. This is many, 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 many iterations. If you use Mathematica, these are all pre-programmed in. I can tell you what, or you can do it. So so John Conway invented this 2D cellular automata rule called the game of life. And basically, I think 0 is dead and 1 is alive. And the idea is that if you have too many neighbors and you're alive, you're going to die because too many people, and nobody likes too many people. No, you're competing for resources, right?
Mm-hmm.
So you die. But if you have just the right number of neighbors, you stay alive. And if you don't have any neighbors, 1 goes to 0 because you're lonely. 0 can, if you get just the right enough neighbors, it can come to life.
Mm-hmm.
So there's this online thing you can play that is kind of fun. And I could get to it. And it's called John Conway's Game of Life. And what it is here's a big old grid, and you can put in, this works better on my computer when I click. You can put in a bunch of live cells. I don't know why I keep doing that. Sorry.
For introduction, sorry, we coded this.
Yeah, this is an easy one to code, isn't it? Right?
Yeah.
And then you can start, and each picture is an update of whatever rule that is being used. And then there are so many kind of fun ones. Whoops, stop. How do I clear it? Start? No.
Previous speed.
I need to say clear.
It's really great.
And then you can put in predetermined ones. That looks kind of boring. That's not it.
Get an exploder.
Let's try the exploder. Small exploder?
Yeah.
Oh, that's a new one, yeah.
Ooh.
And you can make it go
That's-
faster, I
that's
think. Is that what that does? Oh, and then it just goes periodic. Next. And you can do it one at a time. You can just change. So, or you can put in your own rule and your own initial conditions. And so what I do in my classes is I say find a configuration that has period 3. Find a configuration that never goes away. Find a configuration that does this. So you can mess with it. It's a little bit of, oh, and here are the rules. About what becomes populated or not, the game of life. And there are many of those that are online. So that one's kind of boring.
I don't know, it looks pretty.
Yeah, that looks pretty. I mean, figuring it out, let's
Looks
see.
like butterfly.
The Gosper glider gun.
What is Gosper?
I think what it does is it interacts with another one and then sends it off. There's one that...
There's a person who spends his time just like looking for interesting configurations.
It's like human civilization.
It's a bullet
They go
bill.
for a walk.
Oh yeah, the games are like...
Oh yeah, here's a, yeah, this is the same thing. I've read this many times apparently. So that's an example of a 2D cellular automata. And then you saw mine was the probabilistic one. And there are many, many, many things you could do. And in fact, you could make the grid hexagonal instead of square, or you can make a 3-dimensional grid. We proved that the mathematically the results that we have, the 2-dimension is a very good model for the limp system as opposed to going to 3 dimensions. And 3 dimensions we couldn't really see. So 1 dimension you can see the progression, right? Because you just draw the next one. 2 dimensions you have to draw like that. If you stack them on top of each other and could see in, you could see the progression, but that it's not very illuminating.
Do you think there's like, for a given rule, you can make like a polynomial where you just input like, I mean, you have the number, it's binary. You input the binary and it gives you the value of the next row.
So you got me on to next. Oh, yeah, polynomial. Maybe it would not be polynomial though. Or you should
I don't know, maybe not a polynomial, but some sort of nice function.
That's function. Oh, that's...
Well, so theoretically, each configuration of zeros and ones is a state of a Markov chain, and the next state is completely determined by what state you're in. So you could multiply by a matrix to get the next one. So the answer, I think, is yes. But the state space is huge, right? Because it's all possible sequences of zeros and ones.
So if
Which means
your
the matrix would be huge.
basically, I mean, if you have like a set size of input, then it would be easier.
Yeah.
Yeah.
But it would still be huge because of each.
Oh,
Yeah.
So theoretically, yes.
okay.
All right, that's all I got. Well,
Oh,
yeah, that's all I got.
okay.
Any other questions about any of this?
A lot
Yes,
of
Still
I
going?
have a question about that polynomial, the last topic. How the one combination minus one combination, another combination. how do you get that equation?
The zero forcing polynomial,
Yeah.
that one?
I don't understand the second combination.
Oh, you have to, this guy right here?
Yeah, the second combination.
So what you're doing in this is you're taking off the double counting. So you count the number of ways to do something, and then you have to take off things that you've already counted in there.
No, I think.
Is that what you mean?
That's not double counting, I think, because it is combination, so there is no double count. But
Oh, there are. If I said how to take here, I can show you the proof of it.
I mean, so
I think.
like the NI means you're choosing first
yeah,
I,
I know what
right?
does I mean, but I don't understand the second.
The double count, like, wait, what? You don't understand why there is a double counting, or you don't you understand?
The proof of it is
Because I mean, it should be.
no, I
fair.
understand what your question is.
I think the minus means
You're counting the things you leave behind.
Yeah, I think that's minus situation
Should be this.
like this.
Yeah.
Yeah, but I don't understand why it is. I think that's minus.
Let me show it to you. I'm sorry, I don't know off the top of my head. I've forgotten. I have forgotten all the details of all the proofs because those are zero forcing numbers. We want chapter 4.
What's your question again?
The minus that combination.
Yeah, so you're doing NI minus N minus I minus N.
one.
Yeah, because you have to first take the I,
Did the
that's
student
the
do
number,
the
right?
thesis
Yeah,
as
yeah.
part of finding
no,
the...
you're first
Yeah.
trying to get.
Not all of our students do honors theses.
Okay.
Most of them
Wait,
just.
how do I put it
So
in?
the minus means you need to delete the situations like that. But
No, because what you're taking the minus
It's
out
yeah,
is
it's a
actually
nice
like,
it's a nice result.
this
Okay, so they're gonna compute the zero forcing number from I by finding how many non-forcing sets. I think that's what you were asking. In other words, what doesn't work and subtracting it from I, the non-forcing sets of size I, and subtracting it from all possible ways to choose I sets. So the number of forcing sets is equal to all possible sets of vertices of size I. Take away all the ones that aren't forcing sets.
yeah, so why the unforcing sets are n minus I minus 1 I?
So so here it is. So let's see. We have n minus I. So if we have a non-forcing set of size I, you have n minus I white vertices. So that means you color I vertices and you say that is not a forcing set. So the rest of them are white. So if you want to construct a non-forcing set, so you color I vertices, and then the remaining n minus I are not colored, right? So between each of those vertices, you can either insert one blue vertice or no vertices. So so
just basically.
I'm sorry, I'm gonna talk in a circle if I don't